Hello friends, in previous lecture we have studied the relation between sequentially compactness and compactness. So we proved that every sequentially compact metric space is compact with help of Lebesgue number and Lebesgue covering lemma. In this lecture we will study concept of finite intersection property and the relation between compactness and finite intersection property. So, what is finite intersection property? Finite intersection property. FIP, abbreviation FIP. Let XD be a metric space. Let XD be a metric space and C be covering of X and C be collection of subsets of X and C be collection of subsets of X. Subsets of X. Then C is said to have finite intersection property if intersection of finite number of subsets, if intersection of finite number of any finite number of subsets from C is non-empty. That is, for any f1, f2 dot dot up to fn belongs to C, intersection of fi, I equal to 1 to n, this must be non-empty. Whatever choices of finitely many subsets from that collection. This property is known as finite intersection property. Now, we will take the relation between compactness and finite intersection property. A metric space XD is compact if and only every collection of closed subsets of X, every collection of closed subsets of X with FIP has non-empty intersection. So proof. Suppose XD is compact metric space. Suppose XD is compact metric space and C is equal to F is closed in X. Be collection of closed subset of X. Be collection of closed subsets of X with FIP. That is intersection of Fi, I equal to 1 to n, is not equal to phi. Okay. For any F1, F2 up to Fn belongs to C. 1. Claim intersection of F belongs to C is non-empty. On contrary, suppose intersection of F belongs to C is equal to phi. Then intersection of F its complement F belongs to C is equal to union of F complement F belongs to C is equal to, it must be X 2. Okay. Now each F belongs to C is closed, implies G is equal to F complement is open in X for every F belongs to C, and therefore G is equal to F complement where F belongs to C is open covering of X from 2 is open covering of X from 2. Is it clear? Now since X is compact, therefore X has finite subcover. X has finite subcover from G, say G1 is equal to F1 complement, G2 is equal to F2 complement, and so on. Gn is equal to Fn complement. Then what will get? Then union of Gi I equal to 1 to n is equal to X, that is union of Fi complement I equal to 1 to n is equal to X. So this is by De Morgan's law, right? By De Morgan's law. Again here also by De Morgan's law. Therefore, intersection of Fi its complement I equal to 1 to n is equal to X by De Morgan's law. By De Morgan's law, this implies intersection of Fi I equal to 1 to n, this must be equal to phi for F1, F2 dot dot up to Fn belongs to C. This is contradiction to 1. This is contradiction to 1. Therefore, our assumption is wrong. Therefore, our assumption is wrong, which implies intersection of F belongs to C must be non-empty. Must be non-empty. Okay. Now conversely, we will assume that. Conversely, suppose XD is metric space such that any collection of closed subsets of X with FIP has non-empty intersection This is now 3. What is our claim? We have to show that X is compact metric space. Claim X is compact metric space. On contrary, suppose X is not compact. On contrary, suppose X is not compact. Then there exists open covering, say G is equal to G subset of X such that G is open in X such that X has no finite subcover, from G. That is, union of G belongs to G is equal to X, but union of Gi, I equal to 1 to n, not equal to X for any G1, G2 dot dot up to Gn belongs to G. 4. Okay. Now take F is equal to G F set of F is equal to G complement, G belongs to G. Then F is collection of closed subsets of X as F is equal to G complement is closed for each open set G, G belongs to G. Collection of closed subset of X. Moreover, intersection of Fi, I equal to 1 to n, which is equal to intersection of Gi complement, I equal to 1 to n, which is equal to union of Gi complement, I equal to 1 to n. This must not equal to X. This is not equal to phi from 3. while intersection of f belongs to f, this is equal to intersection of g complement, g belongs to g, is equal to union of g its complement, g belongs to g, this must be equal to x complement is equal to 5 from 3, from 4, this is your 6, this is your 5, sorry, this is from 3. Five and 6 gives the contradiction to hypothesis 3. Therefore, our assumption is wrong. Assumption that X is not compact is wrong. Therefore, XD is compact metric space. XD is compact metric space. Okay. So, we will summarize all the results. Theorem. Let XD be a metric space let XD be a metric space, then following are equivalent. So, first one, XD is compact. Second, X is sequentially compact. X is sequentially compact. Third, X has Bolzano-Weierstrass property. 4, X is complete and totally bounded. And 5, every collection of closed subsets of X, every collection of closed subsets of X with FIP has a non-empty intersection. So, these 5 conditions are equivalent to each other. So, we have proved 5 important if and only if conditions for compact metric space. With this discussion, we will stop this lecture here. Thanks for listening lecture carefully. Bye bye.